Test. Okay. Yeah, so as I was saying, we will be talking about centripetal forces. So last time I drawn this picture, right? I mentioned that the centripetal force is whatever force that has the component that points towards the center. So it is not a new type of force. We have learned basically 5 types of force in chapter 2, right? Normal force, weight, the tension, spring, and friction. Friction has static and kinetic versions. Well, we have also learned about drag force and resistive force, but usually this seldom happen in the context of centripetal forces. But in any case, it's not a new type of force. It is some force that we have learned before, so it's over here, right? So the simple example I want to show you is this. So let's say I have an object, or we have a horse that is tied to a pole with 3 meters. So this is maybe something you see at some amusement park, right? And usually they let kids to ride on the horse, and then the horse will go in a circle, right? So the string will make sure the horse doesn't run away. So it will be at most the horse can run in one circle. So this is a centripetal motion, and there exists a centripetal force that causes the horse to go in a circle, and this force is not a new type of force. It is an existing force that we have learned before. It is tension. So from here we can determine the tension of the rope. So the only force that is acting towards the center is the tension. So we start with Newton's law, right? So the Newton's law along the radial direction. Okay, so maybe I should write this out to be clear. Applying Newton's law, second law, along the radial direction. Okay, so that means it's not just x and y, but it's towards the center. So as it goes around the circle, the direction points towards the center. So Newton's law along the radial direction will give you F centripetal, and then mass, and then times the acceleration. So if we are talking about the radial direction, we will take only the radial components. And since I want to emphasize a lot that centripetal force is not a new type of force by itself, for this problem, the centripetal force comes from tension T. And then you substitute mv, the acceleration, right? So the radial acceleration is v squared over r. Okay, so that is the equation that we can apply. So how do we solve this problem? Well, according to the information, the horse goes one round every 13 seconds, so the period is 13 seconds. So from here we can actually calculate the angular velocity omega, which is 2 pi over the period. Okay, and if you put in the numbers, you get 0.4833 around there radians per second. Okay, so from here we can actually convert into omega, because if you recall the formula, right, is v squared over r, and then v is r omega, so we got r squared omega square over r, so you got r omega square. So from this equation we find that T is equals to m r omega square. So this T is the tension. Okay, so this T is the tension. Yeah, unfortunately tension and period is both T, so I just say period, I didn't call this T. T is the tension, so tension is mr omega square. Then just plug in the numbers, right? So if we plug in the numbers, the mass of the horse is 200, right? So 200 kg, right? So we just choose some random numbers. I'm just choosing some random numbers to show you, right? So we got oh yeah, this is 5 meters. Sorry, 5 meters. So we got 5 meters, and then 13 seconds, so it's 0.4833. So if you calculate everything, it should be 234 newtons. Okay, so this is the tension along the rope. Okay, so this is just a simple example to demonstrate to you that centripetal force is not a new force by itself. Everyone is okay so far? So hopefully everything is okay. And I'm not mute. I'm not mute, right? No. No. And I'm still recording. Yes. Good. Okay. So let's go to the example of the lecture notes. So which is example 2.3.1. This is the pendulum that is hanging from the ceiling. Okay, so let me just quickly draw this here. No need to flip to the PDF. Is that I have a pendulum that is swinging at some angle theta. So it's attached to a string. This is my mass. This is an angle theta. And then it's just a string that is going in a circular motion. Okay, so we got a circular motion over here. Okay, so this is circular motion. And then we just want to determine what is the formula for the tangential velocity of the circular motion. So how do we calculate this? So just need to get the component that is towards the center of the circle. So for this problem, right, we always begin by drawing the free body diagram. So let's start the free body diagram. Of course, it is attached to a string, so we got a tension T over here. So we got tension T, and then we got the weight, so downwards to be mg. And then now we resolve the forces. Okay, so we shall take vertical and horizontal. So mg is already vertical, no need to do anything. For this part, the tension resolved will be T cos theta, and then resolved this way will be T sin theta. Okay, and then the radius of the circle is r. So we have two components to solve here. So for the vertical component, this is in equilibrium, right? There's no vertical motion over here. So for the vertical component, we easily have T cos theta is equal to mg. Am I right? So I got my first equation. So my second equation is the horizontal component. Okay, and this is radial. Because if my ball is, or my mass is this way, I will just take the whatever that is pointing towards the center. So this is the radial component. Okay, so for the radial component, there is only one force acting on the mass, which is this direction, T sin theta. Hang on, T sin theta. Right? And then by Newton's law, is mass times acceleration. And since this is the radial direction, so I can use the formula mv squared over r over here. Okay, then should I plug in? So let's give r first. So what is the formula for r? So the question only gave you the L, right? So from here we can determine the L. The radius of the circular motion is just L sine theta, correct? So it's L sine theta. Okay, so L sine theta. So this r is equal to L sine theta. So from here I got the equation that is T sine theta is equal to mv squared over L sine theta. So I got my second equation. Then just eliminate the t because the t is unknown, right? We just want to get the v. So we just take equation 2 divided by equation 1. So on the left hand side I got cos over sine. On the left hand side is cos over sine, and then on the right hand side is mg divided by mv squared and then times L sine theta. Am I right? So the m actually cancel each other, and then I put my v squared over here, and then I bring this, I got gl sine square theta over cos theta, right? So if you want, we can express this as sine over cos is a tangent, and then this is sine theta. So my v is the square root of gl sine theta tangent theta. Okay, so this is my formula. So this is the for if you want the pendulum to be swinging at a certain angle theta, then this is the velocity that it needs to travel. Okay, then yeah, so we got this expression over here. Now notice that for a pendulum, right, you're swinging a pendulum, we notice that always must be this pendulum cannot be perfectly horizontal. What I'm trying to say is that can I make a pendulum that is swinging perfectly horizontal? Let's figure this out. Alright, so what happens when theta goes to 90 degrees? So theta goes to as theta goes to 90 degrees, what happens for tangent 90? Tangent 90, it becomes infinity. So it's impossible for you to go at a perfectly horizontal pendulum, and the reason is pretty obvious, because the reason why this pendulum can undergo this motion, right, is that, well, look at the vertical force. So for the vertical force, right, there's a weight, and then there's a t cos theta to balance the weight. So when theta goes to 90 degrees, cosine 90 is 0. So when you get 0, then there is no force to balance the weight. So it will try to come down a little bit. Then it will come down a little bit until the tension is capable of balancing it. And to have the sufficient tension to balance this weight, we need to go at the sufficient velocity, at the appropriate velocity given by this formula. Okay. Everyone follow so far? So no question? All good, huh? Okay. Okay, just checking. Yeah. Because it is again, as usual, you know, the most common problem is like I'm talking for 1 hour and then actually I'm offline, and then wow, it is yeah, wasting the recording and everything. So that's the centripetal force. And then yeah, I need to open the lecture notes. Hang on a second. So let's go to the example to show you. Okay, so we are here now, and we have just solved this problem. So the next two problem is quite relevant to quite common, and it will explain how cars, the behavior of the cars a lot. So let me bring this up for the recording, and then let me read this example. Okay, so in this example, we have a sports car rounding a flat unbent curve with radius r. Okay, and then the coefficient of static friction is given, mu s. What is the maximum speed that a car that you can drive without sliding? So this is the explanation of why the car can run in a circle, and also it explains why if you drive, right, when you turn, it is safer to slow down when you turn. You do not try to drive too fast when you are turning in a circle, and the reason is because your car will skid, right? So if you know how to drive, you are aware of this. Okay, so if you drive too fast and then you turn, your car will skid. So, and it is more dangerous if you turn too fast in the rain for a wet road, right? If you turn too fast, your car will skid. And now we can explain the physics. Why does this happen? Okay, so let's see. Let's go to our calculation. Okay, so this is example 2.3.2. Oh yeah, you want drift. So drifting is already skidding, and yes, that so if you are skilled enough, you can still control your car when you are drifting. Okay, yeah, initial D or Fast and Furious, car moving in circular motion. Yeah, so as I draw the picture, I will comment that, you know, in the early 2000s, the drifting trend was very popular. In like 2000, 2003, because I think the movie Tokyo Drift came out, and then the community also, like the driving racing community, was like starting to master the drifting, and then all the movies and games are about drifting. Like Need for Speed has a drifting component, Fast and the Furious, Tokyo Drift, that kind of thing, and then Initial D is already popular at the time, right? So yeah, let's try to solve this problem. So I have a car that is turning in a circle that is in a radius r. So let's say I want to go in a circle that is part of a circle of radius r. So it doesn't have to drive the full circle, but as long as you are in this curve, you can define a radius of curvature. So why does the car capable of moving in this direction? There exists a force that must be pushing it towards the center. Okay, so where is the force coming from? just now I draw the picture of a horse. There's a cable, but when you drive, there's no cable anywhere. There's nothing. The only force is the friction with the wheels against the road. So this is the static friction that makes you go into a circle. Okay, so and then we draw the the vertical component is very easy, right? So for the vertical is n is equals to mg. No, not a problem there. And then we try to solve this problem. Okay, so the reason why it's going to a circle is there exists this force. So we can try to determine the radial or the horizontal component. So horizontal in this case means radial also, because we only talking about the radial direction. So in the radial component, the force that is acting towards this is the only radial component is the friction, and then by Newton's second law is ma. So if we are talking about radial component, so just take the radial part, and for this case it is mv squared over r. So from here we got this equation, right? So we got mv squared over r, and this is again where static friction is weird. It will automatically follow whatever is happening to it. That means, right, if you drive your car with a small velocity, then mv squared times r, the friction will automatically become this force, whatever this force is. If you increase your velocity, if you drive faster, if you're still capable of going in a circle, it is because the static friction automatically becomes higher to ensure it's going in this circle. Okay, so until it reaches a maximum. So static friction can only go up to a maximum. So when v reaches the maximum, my static friction becomes the maximum possible value. It is the coefficient times the normal force. Okay, so this normal force for this free body diagram is equals to mg. Okay, let me check if you why is it static friction? Okay, I will come to it later. I will come to it soon. So okay, so static friction, why is it static friction? The main reason is because the car is not sliding. Okay, so no relative motion against the ground. So car is not slipping or sliding. Okay, so that is what you guys are talking about, right? So if you are talking about drift, okay, so drift is slipping. Okay, so we are assuming we are not talking about drifting here, just a normal driving turn. Okay, and when it's drifting or when it's sliding, right, you can see the burn marks on the road. So that is where the drifting and slipping happens. But if there's no like slipping, right, then the wheels only touch the ground and turns over the ground. It doesn't skid over the ground. Then it is just the static friction. Do you get it? Does that make sense? Okay. Okay, so yeah, it's only touching, yeah, it's only rolling, and oh, I didn't know, it is touching the ground, and it is no relative motion against the ground, but it is rolling. Okay, so the wheels are rolling, as always. I mean, the wheels are rolling over the ground, and we will learn more about this later. Okay, but yes, so for now we just imagine it's only touching the ground. Okay, doesn't scratch the ground, doesn't scrape the ground. Correct, yes, not sliding, so no relative motion. Okay, so it's no relative motion, and I think the best way to imagine is we will learn more about this later in the rolling chapter, where, you know, when a wheel turns over the ground, right? So when the wheel turns over the ground, if it's not sliding, right, it only turns perfectly, every point only touches once, and then you continue to roll. But if the wheel is like scraping over the ground, then it is slipping already. Okay, so oh, okay, so that means this they also do this calculation in initial D lah. Right. Anyway, yeah, I should finish this calculation. So when v goes to v maximum, this becomes this. Therefore, mu Sn is mv max squared over r. Oh, I forgot to substitute mg. So I got mu S mg is mv max squared over r. So we cancel the m, and from here we got the maximum speed. that is achievable. The R is capital R, so it's got mu s g r. Is it correct? Yeah, mu s g times the radius. Okay, so it depends on the coefficient of static friction. So for this problem, it's just an arbitrary number. So, but from here, right, it depends on the coefficient of static friction. So you cannot drive faster than this, because if you drive faster than this, then yes, drifting will happen, okay, or slipping or sliding or skidding, yeah, whichever word that helps you imagine. Okay, so and then it depends on G, and then it depends on R. So notice that when R is larger, you can drive faster. Okay, so a larger circle, you can drive more faster on a larger circle, and then if R is smaller, the V maximum will also become smaller. Okay, and it also depends on the gravity of the earth, because the reason why is because the gravity is pulling you and pushing you against the ground, which contributes to your friction, static friction. Okay, the normal force, and therefore static friction. Well, no need, because we are it is understood that we are talking about speed lah, right? We are talking about speed. So negative V means you are driving backwards, but here actually is we are talking about the speed, right? So we did not even define the direction of circular motion. I just draw clockwise motion, but it could be anti-clockwise, so it could be either case, so we don't care whether it's positive or negative, because we did not yeah, correct, just the magnitude. We did not define the direction yet. Okay, even if you draw this direction, this circular motion is then yeah, so that's why it's not important. Any other question? Okay, then okay, so now then let's go to the other part, this other question. Okay, so you may have seen this before. NASCAR racing, I think they call it is popular in America. It's a different type of racing. They just drive in a circle, but they can go very fast, and the track has a tilted angle, and the reason why is to make sure the car can go faster when driving in a circle. So let's see how it works here. Okay, so a car traveling at a certain speed v, it is possible to bank a curve at just the correct angle so that there's no friction needed to maintain the circular motion. Okay, so just now when we solved the problem, right, we were using friction. Friction is the one that causes it to go in a circular motion. So, but for this problem, right, if this angle exists, it's possible that there's no friction. Even on a smooth ground, the car is able to turn in a circle. So then we just need to determine the required beta if the speed is v. See, we are talking about speed, so not the velocity. So let's try to solve this problem. This is example 2.3.3. Okay, hang on, let me get the page. Example 2.3.3. So in this picture we have a banked curve. So let me draw the portion of the road, something like this. Okay, it is tilted at the angle beta, and my car is here. Okay, so it got wheels, but as always we want to treat this like a point mass. Okay, and then it's going in a circular motion. Okay, so it's going in a circular motion of radius r, so something like that. Okay, so let's try to draw the free body diagram acting on this object. So there is a weight as usual. We got mg over here, but my normal force is this way now. So I got my normal force. Let's call this n. So this question is possible even when the surface is smooth. So when the surface is smooth, right, there's no friction. There's only two forces acting on this situation. So now let's try to resolve the forces. So if I resolve this way, I got n cos beta. If I resolve the other way, I got n sine beta. Okay, so the vertical component tells us that well, n cos beta is equals to mg, right? So this is my first equation, and then my horizontal component, which is also the radial component, tells us that the only horizontal force is n sine beta. Okay, and by Newton's second law, this net force is equals to ma, and we are talking about the radial direction. So since this is the radial direction, we can plug in this formula now, right? So from here we conclude that n sine beta is equals to mv square over r. Then this is my second equation. Okay, so from here we can easily calculate the beta by solving these two equations. I have two unknowns, right? Let's say the v is fixed for some v, and then m is all these are constants. So n is the unknown here, right? Beta is the second unknown. So we want to eliminate them. So let's take equation 2 divided by 1. Okay, so if I take 2 divided by 1, this will cancel and it becomes a tangent beta. And then on the right hand side, this divided by this will cancel the m, so I got v squared over gr. So the angle that you need is the inverse tangent v squared over gr. Okay, so for any velocity you plug in, and then for the gravity and for the radius of the circle you plug in, you get the angle that you need to build the road. Okay, so yeah, so this is the answer. Oh, this is Cars 2, right? Or Cars 1? I forgot. I've never watched Cars 2. So the racers, for this case, right, we are actually ignoring the wheels. I think for the bank curve, yeah, you can keep your wheels straight. But for turning, you need to turn the wheels, and so the situation is complicated if you want to relate this to the wheels, because we're sort of simplifying the problem. So I think yes, so if I'm not wrong, right, turning the wheels will cause your wheel to sort of give a radial component to your static friction, right? So if you turn your wheel, all the complicated interaction will work in such a way that there is a net force coming from the static friction. But if you drive straight, then you don't need to do anything, because the road is already bending in that direction. Okay. Yes. So Turu is right. The another condition is you need to be at the right speed, so you don't need to turn the wheel. Okay. So for example, if your road is exactly the angle beta, right, then you need to travel at exactly this velocity. Okay, so just to give you a visual, concrete imagination, right? So it's gr tangent beta. So if my road is banked at 30 degrees, right? So you can calculate this number. Let's say my radius of my turning circle, I don't know. Let's make it 10 meters, right? And then I have tangent 30 degrees. Okay, so let's see how fast do we need to drive. 9.8 times 10 times tangent 30. Okay, so the square root of this is 7.52 meters per second. Okay, so you need to drive at exactly 7.52 meters per second so that there's no friction anywhere. Okay, but if you drive at a speed that is not equal to 7.52, then in order to have a net force to go to this centripetal, you need to have an extra static friction. Okay, and static friction will come from turning the wheel correctly. Does that make sense? Okay. Yeah. So, So this is So this is how we describe this circular motion over here. So this is why cars can drive in a circle. Okay. So I think that is the final. Yeah. This is the last page already. This is the centripetal force. So this is the last topic of chapter 2. Any other question for chapter 2? Oh, you don't understand? Which part? During the bicycle. Oh, the bicycle is even more complicated. The V equals to 7.52. Okay, so for Charles' question, right? For Charles' question, how to say? So at this speed, okay, remember we derived this question by assuming this free body diagram, and assuming this free body diagram means there's only two forces, there is no static friction. So this is the situation that is the result of driving at this speed. So at this speed, there is no static friction is 0. Is 0. Okay, so yeah, and do we have time? So I think, right, this question is too specific already, and maybe it's not clear. So I think what I'm going to do is, let me solve a more general problem. Okay, so so at this speed, static friction is 0. And remember, right, static friction is automatically responding to what is happening to it, automatically adjusts itself from 0 to a maximum. Okay, so yeah, I'm going to talk about the bicycle soon, later, but let me try to solve this problem in a more general situation. Okay, so let's call this theta now. Okay, so it could be any angle, and then my car is driving in a circle. Okay, and then I have static friction. So static friction, right, again, is automatically responding. In fact, it can act in this direction or it can act in this direction. Okay, so let's assume it's acting in this direction first, my static friction. So this is my static friction force. Okay, and then this is my normal force here, and then I have the usual weight mg coming down. Okay, so if this car is driving in the circular motion, then I can resolve my forces. So this is still n cos theta, and then this is n sine theta, and then now I have this force, static friction. So the static friction also can be resolved. So right now I got Fs, this is cos theta, right, and then the downwards component is Fs sine theta. Okay, so now let's try to solve this system. For the vertical components, okay, what are my vertical forces? So my vertical force is this, and the mg, right? So all these are my vertical force. So the upward is this, balanced by my two downward forces. So I got n cos theta is equals to F sine theta plus mg, right? So from here I got yeah, let's keep it in this form. Okay, so let's keep it in this form, right? So the vertical force balance the downward force, and then for the horizontal, what is the horizontal? So the horizontal force is this force and this force, only two, right? So I got n sine theta plus Fs cos theta is equals to the mass times acceleration by Newton's law, and this is the radial direction. So this is mv squared over the radius of my circular motion. Okay, so then what I want to solve this equation for static friction. So let's try to, I'm just trying to think of how to rearrange this in a nice looking way. So let me rearrange it in like this. So n sine theta is mv squared over r over Fs cos theta. Okay, so 2, right? And then, so by the way, right, this is the part I spontaneously decided to do, so I did not prepare this. So that's why you see the difference between solving something in real time. I'm deciding how to rearrange my equation and things like that. So this is probably what your thought process will go through in solving the exam and things like that. Okay, so I decided to arrange my equation like this. I don't know whether this is nice or not, but what I can do is I can cancel the n now. So I can cancel the n by taking equation 2 divided by 1. So let's take 2 divided by 1. Okay, so 2 divided by 1, the left hand side will become tangent theta. And then on the right hand side, I got Fs sine theta plus mg. And then on the right hand side, I got mv squared over r minus Fs cos theta. Okay, so I don't know whether this is correct or not. Yeah, so let's try to solve this for Fs. Okay, so I will keep this equation. I'm going to come back to this later, but now let me rearrange this a little bit more. So I got mv squared over r tangent theta minus Fs tangent times cosine is sine, right? And then I got Fs sine theta plus mg. Okay, so I hope I did not do any mistake here. Yeah. So if I times everybody, yeah, so let me just bring this over first. So I got 2Fs sine theta plus mg, and then this is mv squared over r tangent theta. Okay, so I can solve this equation for Fs now. So 2Fs sine theta is equal to mv squared over r tangent theta minus mg. Okay, so so from here we can see that my static friction, right, is automatically obeying this formula, the magnitude at least, minus mg. Okay, so from here now I can derive two conditions. Okay, because this static friction cannot be larger than mu s times the normal force. So the normal force is now given by this formula. Okay, so so it cannot be greater than this force. So but for whatever speed you're driving, the static friction will automatically responding to this. So if we want static friction to be 0, then this whole equation to be 0. So we conclude that mv squared over r. I think my tangent is in the wrong place. Hang on. Yeah, see, so so my tangent is in the wrong place. Let's see. 2 divided by 1 is tangent. Oh, this equation is upside down. Yeah, I messed up already. Hang on. Wait, sorry to waste time. So if I take equation 2 divided by equation 1, so this is tangent theta. So 2 divided by 1, so mv squared over r minus fs cos theta, and then this is f. No wonder it felt a bit wrong when we are deriving it. Okay, so we got this equation. Okay, so you can solve for fs if you want. Then you get some formula, right? And this is where all forces are playing their roles. Okay, so this is in the general case. Then if fs is equal to 0, then I got this equation. So tangent theta is equals to, this is 0, this is 0. So we got mv squared over r divided by mg. So cancelling this, then I come back to the original calculation. Okay, so that is how we got this. Hang on. That is how we got the. This is the wrong one, so I'm not going to scan this. Okay, so yeah, so this is the we rederive the formula. Okay, so I don't know if I made any sense because I made a mistake over here. Yeah, so this one was just now, right? So I did it wrong just now. Okay, so 2 divided by 1. Okay, so so what I did was I derived the most general case for any velocity, because if you want to go for any velocity, then there could be some static friction. Okay, but for only a specific velocity, then you will get a 0 static friction case. Okay, for this specific velocity. Then yeah, so basically that's the solution. Okay, then for the bicycle question is more complicated, because for bicycle, the bending part is something we haven't talked about yet. The bicycle, right, is we are talking about wheels. So wheels have angular momentum, and then angular momentum, it will have a friction with the ground also. But the bending part is that if you bend over, then yeah, so if I draw on this side, right, so your bicycle is the seat, bicycle seat, and then the handles, and then so if you bend, then the same. Okay, if you ignore the angular momentum stuff, then yes, if you want to turn to the right, if you lean over a bit in this direction, then there's going to be generally some kind of net force over here. Okay, then it will make it go to the to the circle. And why is it leaning this way? It's very hard to answer because you need to see the detailed orientation of the materials. This is rubber, so the rubber is like squeezed in one direction, but it's not squeezed, so it's very complicated, right? But generally speaking, that since we know that the bicycle is turning in this circle, then we know the net force is in the direction. We can identify the net force in this way. Okay, what is this? So hang on. Okay, any other question? What is this picture? It's the same, right? So n sine theta, n cos theta. I think I'll look at it later, right? So the force. So this is n sine theta, okay, and then it's the same as just now, right? So hang on, why is it wrong? So n sine theta, because this is my theta, right? This is my theta, and so to avoid looking at triangles, right? The simple way I imagine is, let's see what happens when theta is 0. So when theta is 0, there's only the vertical component left. So cosine 0 is 1, right? So you got purely n over here. And then when theta is 0 or small, then sine theta will become small. So for a smaller angle, this component is expected to be small. So this is how we resolve the thing. Oh, okay. I think I'll look at it later lah. I think for now we better look at the next. We better start the next chapter already. Okay. Otherwise we drag too long. So now we are talking about work and energy, right? So this is the next chapter. Okay. So now we talk about work energy. Okay, so I let you guys discuss. Then I will continue talk about work and energy. So I'm still recording. Yes. Teams is recording. Yes. Okay. We are now in chapter 3. Okay, so chapter 3. Maybe new page. New page would be nice. Chapter 3. So now we're talking about work and energy. Okay. So what is work and energy about? We shall start by talking about work first. And this is the logical, this is the conceptual way. By defining and understanding work, we will come towards the conservation of energy concept. And so now about energy, right? This is something that everyone always learns since secondary school or high school, is that energy is conserved, right? And even in kids or in other places, they say that energy is something that cannot be created or destroyed. Okay, so we're trying to come. We will try to eventually approach this topic now. Okay, why is it cannot be created or destroyed? And actually, this is a very fundamental and deep topic in physics and also mathematics. It turns out that actually, right, the reason why energy cannot be created or destroyed is actually coming from mathematical concept. Okay, so this is where this is the content of Noether's theorem. So the math student might be interested in this because Noether, right, she's a mathematician around the time of Einstein, and she works in algebraic geometry. So the math student might encounter Noether's other theorems in like algebraic rings and fields and things like that. Then Noether derived one theorem that is important for physics and is to do with the conservation of energy. So according to Noether, right, the reason why energy is conserved is because there's some symmetry in the system. So what is a symmetry? Symmetry is something that if you apply a transformation, the system remains the same. Okay, so that is the symmetry. For example, if you look at a mirror, right, it's a reflection symmetry because your left-right changes. Okay, a circle is symmetrical because if you rotate the circle, it still looks like a circle. Okay, and same for a sphere or a cylinder. That one we call it circular symmetry. Okay, so then we have different types of symmetry. Circular symmetry, reflection symmetry, translational symmetry. So all this will be related to some kind of conservation law, and I will talk more about this as the time goes on. But for now, let us note that what are the kinds of conservation law we will learn. We will learn about linear momentum, conservation of linear momentum, and we will learn about conservation of energy in this chapter, and later we will learn about conservation of angular momentum. Okay, so energy is the symmetry in time, the time direction. So because the laws of physics in the past and in the future is the same no matter what, Newton's law is still Newton's law whether you are using it today or yesterday, right? So, and actually that will give you conservation of energy. Conservation of linear momentum is the direction. So if your system is symmetrical in a certain direction, you got conserved linear momentum. And then angular momentum is rotational symmetry. Okay, so we're going to learn about this now. But to start with, right, we have to start with the concept of work. So let's talk about work. And we will first start with the simplest case. What is the work done by a constant force? Work also is something you learned before in the high school, right? It's the force times displacement. And we will define this more precisely, okay? So let's look at the constant force case first. Let me just double check if there's any other question. You guys are, okay, I will check this later because yeah, I will let you guys work this out. Okay, so because we don't want to drag too much time, I need to start chapter 3 now today. And so let's define work done by a constant force. So constant force, let's say I have an object. Okay, so this object is having an initial position, and then it is experiencing a net force that is maybe in this direction. Okay, so I'm drawing a vector now because force is a vector, right? I'm not resolving this yet, but let's say at some later time the object has shifted to here. Okay, so object has shifted to here, then the displacement is another vector like this. Okay, so these two vectors may or may not be in the same direction. Okay, I purposely draw it in a different direction here, but if the angle is 0, then it is the same direction. Then so generally speaking, right, the displacement is equals to my final position. This one we did this in chapter 1, right? Minus initial position. Okay, so my vector S is my final position minus initial position. You can write the xy coordinates for this. So you got the displacement. Okay, and then the force. So sometimes we also use this notation. Okay, the force is just F. So that's all here. But what is the work done in this case? So the work is a quantity we purposely define to be the dot product between the force times the displacement. Okay, or sometimes we say that we use the notation delta R. Okay, so this is the work done. Okay, so that's the work done, and then this is the vector notation, right? So this is the vector notation. What notation I call this? Oh yeah, so if there's another notation is by looking at the magnitude, right? So if my magnitude of the force is just F and the magnitude of my displacement is delta R and the angle between the two vectors is phi, then the work done is using the second formula is just F times S cosine of the angle. Okay, so this is the definition of work. So now I think, yeah, so this is a new quantity, so I should talk about the dimensions a little bit. What is the dimension and the SI unit? So dimensions, let's look at the dimensions of work. So the dimension of work is just the dimension of force times dimension of displacement. Dimension of cosine alpha, this one is dimensionless, so it just put it as 1. Okay, so the force is mass times acceleration, right? So it's mlt minus 2, and then the displacement is another L, so the dimension of work is ml square t to the minus 2. Okay, so from here we can get the units. Okay, so the unit is m is for SI is kg, this is meter square, and then this is second square, and the familiar units is, we call this 1 joule, right? So this one is, we know to be the unit of energy. Okay, so this is the unit for work and unit for energy, they are the same thing, we call it joule. Okay, okay, so Kaheng wants to explain why this picture resolving is wrong, right? Okay, I will look at it later, or if someone can explain also good. So I guess how saw what's wrong with the force, right? Yeah, so I'll let you guys to figure this out for that part, but for now let us look at the first example of work. Okay, so this is a simple example. This person exerts a steady force given the magnitude on a stall car, and then the distance is moved by 80 meters. So yeah, flat tire, blah blah blah. The main point is that he needs to exert this direction to make it go at this angle. So the force and the displacement is not the same angle. Okay, so let's try to work this out. 3.1.1. Okay, so for this problem, for part A, my car is moving at this displacement, but my force is at an angle of 30 degrees, right? So my force is this way, and then this is 30 degrees. Okay, so the work done in this situation is just the magnitude times this magnitude and then cosine phi. So for this problem, it is 210 newtons, and then the car moved by 80 meters, and then cosine of 30 degrees. So the work done in this case is 3.3 times 10 to the power 3 joules. Okay, so this is the work done for part A, and then part B is just to teach us the vector notation. So if he is now exerting the force of given by this vector 160 I direction minus 40 J direction, and then the car displaced by 14 I plus 11 J, then the work done is just the dot product between F times S. So the dot product is very easy. If you have the components, it's just 116 times 14, and then this is minus 40, and then 11. So if you plug this in, you get 1800 joules. Okay, so just like that. Okay, so this is the force of work done in these two situations. Okay, so one thing to observe is that my work done formula, right, is this Fs cos phi. So work done is 0 if my force is perpendicular to the displacement. It is because my angle is 90 degrees. So cosine 90 degrees, sorry, cosine 90 degrees is 0. So work will be 0 if this, and then it's going to be negative if my angle is between here to here. Okay, and positive if yeah, so 0, phi, 90. Okay, so these are the expected cases, right? So if my object is displacing this way, and then my force is acting 90 degrees, then this is 0 work done. So this force doesn't do any work on this object. Okay, so the work done is 0. And then if my object is moving this way, and then my force is this way, so the work done is negative. But if they are generally pointing towards the same direction, then only you will get a positive work done. So this actually, this F cos theta, right, you notice that this one is just measuring the component of the force that is contributing towards the direction of motion. Okay, so this is why you get positive, negative, or zero. So negative work done means the force is doing, the force is working against the motion of the object. This is contributing towards the motion of the object. This one, nothing, right? Zero, no effect. Okay. Okay, so still talking about this. Okay, so how about let us take the break time now, and then I will show you the picture again. Yeah, it's okay because now it should be a good time for the break, and we will come back in 15 minutes. Okay, so let's stop the recording. OBS is here. Never mind. Just record. Test, 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 test. Okay. Okay. So the next. That sound fine. Okay, thanks. At least the Teams is okay on Teams lah. So let's see how to apply our formula by a very, very simple example. So this is an extremely simple example, but I'm going to come back to this to show you two different methods of calculating work done. Okay, so for this one is the following. A force with magnitude Fx horizontally to the right. Hang on. X horizontally to the right and pushes a mass up a platform. So this is one situation where the force doesn't need to be the same direction as your displacement, because I have a platform, right? So I have a platform, and even if I purposely try to push something to the right, right? Even if I purposely try to push something in this direction, but my box will go upwards along the platform. Okay, so what is the work done during this process? So let's try to work this out. Okay, so what's the work done during this process? We just need to get our two vectors. Okay, my displacement vector is over here, and then my force vector is over here. So the angle between these two vectors is this. So I have shown you two formulas to apply the work done, right? So let's look at the first one. So for the first method, the work done is just Fs and then cos of the angle between the two of them, right? So the force magnitude is F naught, and then the displacement from here to here is just L. So this is the angle between them is alpha. So the answer is Fl cos alpha. So this is the first method. Is probably the method that you learned in the high school, correct? So this one, no problem. How about the second method? So the second method is probably newer to some of you, but it's more important to learn now, because this is where at higher level this method will be more convenient, which is to write this in vector form. Okay, so to get the vector form, I need to express this in vector notation, and again I will choose my axis. So I will do this choice. Okay, that means my horizontal component of my F is the magnitude cosine alpha. This is the I component, and then the vertical component is sine alpha j. Okay, then I got this, and then my displacement vector will also have the components. My displacement is going this way, so the horizontal component, it travels horizontally by how many units? It is L cos alpha, and travels vertically by L sine alpha, correct? And therefore the work done is just the dot product between the two. So F dot S, so this times this is Fl cos square alpha, this times this is Fl sine square alpha. So cos square plus sine square is equals to 1. So the answer is also Hang on. Wait. What am I doing? What am I talking about? My force is horizontal, so yeah. So this, right? So this is wrong. Then I'm sorry. Yeah, for some reason I went to solve the second example straight away. So the force is only one component. Then the dot product between the two is just FL cos alpha, which is the same as before, right? So this is what we expect. Okay, so it's the second example I was doing, 3.1.2. Okay, so in 3.1.2, right? So I have my box is still on the same platform. Okay, so it's going from here to here, but this time my force is pushing it this way. Okay, so my force is pushing it this way. The distance is this. So the method 1 work done, 3.1.2, is it correct? Yeah, it's this example, right? Yes. So for method 1, the work done is FL S0 times L. Okay, so for method 2, I need the in vector components. So now, right, again, I resolving it this way. So my horizontal component is F cos alpha I, and then F sine alpha j, and then my displacement is this part. So it's the distance cos alpha I, the distance sine alpha j. Okay, and then the dot product is this. So it's this times this. I got FL cos square plus FL sine square. So cos square plus sine square is 1. So is the final answer is just FL again. Okay, so the two methods should give you the same answer regardless. You can choose whichever one is more convenient. For this example, obviously straight away we know the answer, but I purposely show you this method to get used to our vector expression. Okay, because more difficult question will require vector expressions. Okay, yeah, so thanks everyone for contributing to the discussion. This is good, right? So so 3.1.2 done, and what's next? No, this is 3.1.3. 3.1.3 is the one that we just did. So 3. Then let's now talk about the next problem. Okay, so in this problem, right, I have a box of mass 2 kg ejected across a rough surface with initial velocity 5 meters per second. So let me write this down, 3.1.4. Okay, so I have a box of mass 2 kg. So let me say my mass is 2 kg. My initial velocity is 5 meters per second, and the coefficient of kinetic friction is 0.2. Okay, so what is my displacement of the box after it has stopped, and what is the work done by kinetic friction? So let's solve this question. Okay, so I have a box over here that is ejected initially at 5 meters per second. Okay, and this is a rough surface, so it will slow down, and it will slow down because of the kinetic friction. So there is a force acting on this is Fk, right? So Fk, the formula for Fk is coefficient times the normal force, and then we have the weight, and the normal force for this case is equals to the weight, right? So if you look at the vertical components, okay, so yeah, so based on the discussion that we just had, right, with everyone just now, let's be more careful. The net force in the y direction is taking upwards as positive, so we got n minus mg, and then is equals to mass times the acceleration, but for this case is 0, so n is equals to mg. And then you look at the horizontal. Excuse me. Okay, so horizontal components. So for the horizontal components, my net force in the x direction is only this one, and it's acting to the left. So it is a deceleration. So this is Fk, and this is the m times the horizontal acceleration. Okay, so this is basically just mu k times the normal force. This is m, the horizontal acceleration, and then I can plug this in. So I got minus mu k mg, and then this is mg max, cancelling the mass. So my acceleration in the horizontal direction is mu k times g. Okay, so so I have solved the system, but actually what is the question asking for? The question is asking for the work done or total displacement after it has stopped. So I want to find displacement. Well, I do know the acceleration. This is a constant acceleration. Therefore, I can use the kinematic equation, right? So the kinematic equation for displacement is this. Well, I don't care about the time, so I just use this equation. So v squared plus v naught squared is equals to 2a, and then the horizontal displacement, right? So I want to find after it has stopped. So this is 0, and then this is my initial velocity, and then this is 2 mu kg, and then my displacement. So my displacement is my initial velocity divided by 2 mu kg. So we can actually get this number. This number is 6.4 meters. Okay, so this is my horizontal displacement. And then the next thing is to get the work done. So the work done is very easy because, again, I'll just teach you the vector notation. The displacement vector is S, right? So S is the only got the horizontal displacement, and we have found the horizontal displacement, which is just positive 6.4. So I got v squared over 2 mu kg. I got the magnitude, or in other words 6.4 meters in the I direction. And then the force acting on this is only the kinetic friction, and then the kinetic friction is just minus mu k mg minus in the I direction. Okay, so from here we can calculate the work done. So the work done is equals to the force dot product with the displacement. So I got minus mu k mg, and then dot product with this. So I got v squared over 2 mu kg, right? And then from here we actually cancel the mu g, and then I got minus half mv squared. Okay, so why does this look so familiar, right? This is half mv squared. Okay, so this is familiar, right? You seen any questions so far? So you may have recognized this as a kinetic energy. And why is this half mv squared? Is because of a theorem that we will learn later. But for now, we just want to answer this question. So what is the work done? If I plug in the mass and the initial velocity, I will get 25 joules. Okay, so this is something like a kinetic energy. And why is it negative? We will come to this next. Okay, so any question? Wait now, let me get something while you, if you have any question, go ahead to type. Let me get something. Okay, so everyone is okay with this example, right? So now let's continue with the next one. Constant deceleration. Well, it doesn't depend on time. If we calculate the acceleration, right, it's a number times another number which is constant. The coefficient of kinetic friction is fixed depending on the material. And obviously, you do not change material halfway through the motion, so they do not change. Okay, so these are fixed numbers. Okay, any question? Any other question? If not, we go to the next example. So this is another example but now involving gravity. An object of mass m falls vertically under gravity from a height of this much to this much. Calculate the work done by the force of gravity. Okay, so let's compute this. Okay, any other question? Okay, so yeah, so now let's calculate the work done by gravity. So this is example 3.1.5. okay, according to the question, let me just choose upwards as positive. Okay, so I have a box that is initially at this plus this number, and then it falls towards this height. So purposely they chose this height to be this number h. Okay, and what is the work done by gravity? So let's write the vector. Okay, so again I'm going to solve everything by vector notation. The force due to gravity is the weight, right? The weight is mg. But is my sign correct? If I chose this to be my positive axis, is negative mg in the j direction. So the force is pulling it downwards, obviously, right? So this is my force. How about my displacement? So the displacement is initially this position, and then later it goes to this position. So it is how to write final position minus initial position. So we should say that final position minus initial position. Okay, so we don't care what is the x coordinate, right? So let's say this is x equals to 0. This is the origin here. So my final position is y naught. So it's y naught j. Okay, minus my initial position is y naught plus h. So y plus h j. Okay, so the displacement is actually negative h in the j component, right? So this minus this will cancel the y0, and then I got negative h here. Okay, so the negative sign is where you need to be careful. So both terms have negative, so the work done is F dot S, then will give you the correct answer, which is minus mg times minus h. So the answer is mgh. Okay, so the work done by gravity is positive because the force is the same direction as the displacement, so you got the positive work done. Okay, and again you see something very familiar. What is this? This looks like a gravitational potential energy, and why is this appearing here is we will learn this in the work energy theorem next. Okay, now so everyone is okay with the concept of work so far, right? The examples that we have solved are easy because the work done is constant. So now let's start to talk about variable force. Okay, variable force and arbitrary displacement. So this is where it gets more complicated, more mathematical formula. So let's see what happens. Okay, so if F is not constant, how to solve? Okay, we do know about non-constant force because, for example, the Hooke's law is not constant force, right? Because it changes depending on your position. So this is an example of a non-constant force. So if F is not constant, how do you do it? So let's try to draw this situation. Okay, in fact I can draw any arbitrary displacement. So let's say my force is, my object is initial position here, so initial here, right? And then let's say maybe this is my final position. Okay, and then at different points the force is different. So how do we solve this? So I'm going to separate this into different segments. Okay, so different parts. And then in this part my force is acting this way, in this part my force is acting this way, and then some other direction, could be anywhere, right? So it could be any possible direction. So this is F1, this is F2, and so on and so forth. Okay, so if it's not a constant, right, then what you can do is I will separate this into small pieces. So if I separate into small pieces, then let's look at the first component, the displacement from here to here. So for this S1, right? If this is a small enough displacement, then my force is approximately constant. Okay, then over here for this displacement also is approximately constant, and then this is approximately constant. Okay, so we divide the motion into smaller parts. Okay, so I have my displacement, I should call this R. So smaller parts delta, smaller parts which is delta R1, delta R2, delta R3, right? Many pieces. Okay, and then if my parts is divided small enough, then F during that part, right? F during that part is approximately constant. You get what I'm saying? Okay, so that means, right, then I can use F dot delta R. Okay, so because originally, right, we assume F is a constant, then we can calculate this. But if F is not a constant here, then which value to put in here? So we don't know yet. But what we can avoid this problem by dividing into small pieces, and then during this piece, then this is approximately a constant. So that means the work done is approximately the force here times this part, and then the next part times the next displacement, and so on and so forth, right? So basically the notation that we use is the summation from 1 to n, okay, Fi dot delta Ri. Okay, so now this approximation is accurate, more accurate, as this one gets smaller. So maybe the MAT people will see where this is going. This is like a Riemann sum, right? So that means the approximation is perfect. The formula will become perfect or exact as we take the limit. This term goes to 0. Okay, so this term goes to 0 means what? This is like a integration. So what I'm trying to say is that the work done is the integration with respect to displacement. Okay, so now this formula may look very scary because this is not a normal integration. This is an integration involving vectors, but actually if you plug in the formula, in the end it just becomes a very simple formula. Okay, but at this stage, let's see how is everyone now. Everyone is following so far, I hope. Okay, I'm recording, right? Yes, and I'm recording here. Testing. Yes, I am. Okay, so if everyone is still okay, I will elaborate even further. Okay, so how do I make use of this formula? So now this is the general formula for work done for a non-constant force. If it's constant, it's fine. If it's not constant, how do we use this? And then how do we use this? So let me teach you how to use this formula. Okay, so this is a force vector. So force vector, always remember, it has a, let me assume two dimensions first. Okay, so let's say it has two components, x and y. Okay, so just put it in this way. Then for this one, right, this one is just what I mean by saying dr is just the small displacement in x plus a small displacement in y. Okay, so it just means this. So what happens if I plug in everything? So if I plug in everything, right, I need to calculate f dot dr. So what do I mean by f dot dr? So f dot dr means, so is f dot dr, it just means that I have an x component and I have a y component, and then the dr means I have a small x displacement and a small y displacement, and then if I dot the two together, I just get fx dx plus fy dy. Okay, so the integral of f dr would give you the work done. It just means that you just need to integrate these two terms over here. Okay, so basically you just need to get the x component, and then you integrate along the x direction, and then you get the y component, and then you integrate along the y direction, and that will give you the work done. Okay, is everyone okay? Okay, I'm still online, right? So yeah, I assume so. What time is it now? Okay, so this is page 10. Let's see how we make use of this formula by an example. Okay, so variable force. The first example is the one involving spring. So calculate the work done by an external force F in stretching a spring from its equilibrium position to a new position at constant velocity. Assume all motion is along the x direction. So this is example 3.1.6. Okay, so let me draw this picture. Okay, so in this problem, I have a spring that is in the horizontal direction. Okay, so initially my spring is in equilibrium position. So equilibrium position, we put this at x equals to 0, right? And then I am pulling the string with an external force. Okay, an external force at constant velocity. So why is this two statement important? I have actually two forces here. I have an external force of this magnitude in this direction, and then because this is attached to a spring, right, I have Hooke's law. So I have Hooke's law, the magnitude is kx in this direction. Okay, so I have two forces acting. Spring force F spring is acting to the left kxi. Okay, and then I have the external force, which I call Fext. It is some magnitude acting towards the right. Okay, now according to this question, right, well, let's first let me say the net force. So the net force is F external. So all the forces acting on this system, right? So basically I got F external I minus Kx I, right? So over here I got F external minus Kx in the I direction. So this is my net force acting on the system. Okay, but yeah, so again, related to the discussion that we had during the break, we always talk about net force, but this is Newton's law. Newton's law have left hand side and right hand side. We don't forget about the right hand side. So according to Newton's law, right, the net force is equal to mass times acceleration. And according to this question, this object is moving at constant velocity. So A equals to 0 over here. Okay, so which is to say that my external force magnitude is equal to Kx. Okay, so if I look at the vectors, this is the I direction. Okay, so I have my formula for therefore I have derived the formula for my external force now. So my external force is Kx in the I direction. Okay, it's constant velocity because it's perfectly cancelling out the spring force, so that the spring is moving at constant velocity. The mass is moving at constant velocity. Okay, so do you follow so far? I hope I'm still online, because there's nobody talking here suddenly. I think I'm online. Yeah. Okay, good. Thanks. Yeah. Okay, thanks. Need to check. So now, the question is asking to calculate the work done in moving from here to here. So this is my displacement. Okay, so the distance is from here to x naught. Okay, so I need to know my displacement vector. Okay, so my displacement vector is dr. So dr is just dxi, and then there's no vertical motion. So I just need to do this. Okay. Why is Kaishan? Yes, correct, because ma is 0 and it's moving at constant velocity. Yes. Yeah, that's right. Okay. So so now we agree that constant velocity, we got this formula now, and then now we calculate the work done. So the work done, okay, we follow the formula exactly as it is f dot dr. So I got my f here and I got my dr here. So my f dot dr is, this is kx I, dot product with my dr is just dxi. So dot product I dot I will just become 1. So all I need to do is integrate kx with respect to dx. Okay, and according to the question, I need to put in my initial and final position. So my initial position is at equilibrium point 0. My final position is at some position x naught. So k is a constant, so I don't need to integrate the k. It's a spring constant, right? So what you get here is that half x squared from 0 to x naught. So I got the answer is half kx0 square. Again, something familiar, right? So this one looks like the spring potential energy. Okay. Okay. So this is the work done by the external force. Okay. So this is not the work done by the spring. So the work done by external force, you put in the external force, you get positive this number. If you calculate the work done by the spring, the question didn't ask, but let's say if you calculate, this is the work done by external force. So what happens if I try to calculate the work done by the spring? So work done by the spring is what? So the spring force is negative kxi, right? So the work done is the integral of negative kxi, and then the displacement vector is still the same, right? Same situation. So it's negative k integral from 0 to x naught x dx. So you get a negative answer. So it's half kx0 square. So this is the work done by spring. So what I want to say here is that each force, you can calculate their own work done. Okay, so the total work done by the system is 0, because the spring force negative work, the external force positive work. So they two cancel each other out, and also which is also why the velocity did not change. Okay, clear so far? Any other question? Okay, so I have maybe there's one example, but I think I can skip lah, because now this 5 minutes is a perfectly just enough time maybe for me to talk about the work energy theorem. So the next example, so this example, yeah, this is the same problem, but I do not start from 0, but you should be able to get the same, you should be able to get this no problem. And then the next example is solving 3.1.2 again, but using the integral formula. So this one is for you to practice the integration. What I want to do now is to talk about the work energy theorem. Okay, so just enough time to end the class with the work energy theorem. So work energy theorem. So this is section 3.2. So work energy theorem. I mean, we call this theorem lah, but for the math people, you will feel that this is not a proper theorem by mathematical standards. I know, right? But it's to show a relationship between something. So let's start by looking at one-dimensional motion first. So let's look at the 1D case. Okay, because this is a simpler case, so we need to understand the simple case first before we can move on to more complicated situation. So what's the work energy theorem about? So let's look at considering a motion along the x direction under this object is under some force which is F. Okay, and we have learned that the work done by this force is going to be integral of f dx. Okay, so that one not a problem, right? Nothing special there. Now let's make use of Newton's law. So by Newton's law, right, in particular second law, F is equals to ma. Okay, so if I plug this in, then my work done is the integral of ma dx. Okay, so this is an integral of a with respect to dx. These are different variables, so we need to make sure there are something that I can integrate. So I want to do this by applying the chain rule. So applying the chain rule, which is to say that, remember, right, my acceleration is the derivative of velocity with respect to time, but my variable here is dx. So what I'm going to do is I will purposely say that this is dv dx, and then this is dx dt. Okay, so this is the chain rule, right? So this one is something that you learn in calculus, but the main point is I will substitute this formula into my integration now. So what I have here is that this is the integral of m, and then this is dx dt, and then this is dv dx, and I want to integrate this whole thing with respect to dx. So then in calculus also, this one is just changing variables to dv, am I right? Okay, and then this one is just the dx dt is just velocity. So I have managed to change my integration variable to be just mv dv. Okay, so I changed my variables of integration already. Then I can put in my initial and final variables. This is variable v, so we talk about my initial velocity, and then we talk about my final velocity, and then m is a constant, of course, assuming the object doesn't suddenly change mass during its motion. So all I need to do is I need to integrate v with respect to dv. So I got half v square, and then the initial and final limit is here. So the work done is half m final v square and half m initial v square. Okay, so this is where you learn as kinetic energy from your high school, because we concluded that integrating this, the work done is equals to a difference of two quantities that appearing in this combination. So this is where we define the kinetic energy of a particle. So for a particle of mass m, particle or object of mass m moving at velocity v, right? So actually the speed, right? This is actually the speed. Only speed is relevant because v square, right? Then my kinetic energy is half mv square. So for any velocity and any mass, I define this to be my kinetic energy. So if I define this to my kinetic energy, then I can simplify my language, which is to say that the work done is just the final kinetic energy at this moment and the initial kinetic energy. So from here, then so how to say? So therefore, my work done is the kinetic energy at this point and the kinetic energy at this point, right? So in other words, this is the final kinetic energy minus the initial kinetic energy. Okay, so that means this is the change in kinetic energy. So this is our work energy theorem. So the conclusion that we get is that the work done on an object is equals to the change of its kinetic energy. Okay, so this is my work energy theorem. Okay, so it's not a real theorem by mathematical standard. It's just that work energy is equals to something minus something, and then we purposely define this to be our kinetic energy. Okay, so any questions so far? Okay, so yeah, so now it's 11:52. I guess should be time to end for today's class. So anything to tell you? So I think that's all we have for today. We shall continue the three-dimensional case. So this is only assuming motion along the x direction, but of course, generally speaking, my object and force can be in any vector, right? So when we continue on Wednesday, we will consider the general three-dimensional case, but the work energy theorem is still the same. And then also I will do the tutorial question, because I still haven't done the tutorial question about the static friction, which I believe you will find challenging, right? So on Wednesday we will do that. Okay, so I think that's all for today's class. Anyone else have any question? Okay, so yeah, so if there's no question, I think that should be all for today. So everyone's okay, huh? Okay, good. So let me stop the recording. Okay, thanks. So I'll stop the recording, and then I will stop the OBS recording.